advantage. N2 is a very good living group. We know that because nitrogen is there so much in our atmosphere. Okay. So nitrogen can come out very easily, very quickly. Okay. So we take the advantage of this good living group tendency of N2 plus N2, which comes up. We can put the group of our need in that place. Okay, in place of N2. So how do you prepare diazonium? That's what we need to discuss. So first of all, you should start with a benzene ring, and you should put NO2 first. Okay, and how you are going to put NO2, Samira? What this reaction is known as? Yeah, this is known as nitration. Okay, you take HNO3 and H2SO4. HNO3 is actually OH and NO2, and H2SO4 pulls out that OH from HNO3, and that's how NO2 plus is generated. That NO2 plus get attached itself to the benzene, and that's how you get the nitrobenzene. You do the reduction of nitrobenzene. Okay, and when you reduce the nitrobenzene, it turns it into aniline. Okay, how you do the reduction of nitrobenzene, that you remember? Samira, do you remember how you reduce nitrobenzene? Yeah, here it is represented by H. Actually, you take tin and HCl. Okay, metal HCl. Okay, and you keep the temp, and this is aniline. This is the preparation of aniline. Aniline you react with NaO2 plus HCl, and that's how you get the diazonium. And this diazonium is a very good living group. Okay, yeah. So you can put the nucleophile of your desire. Okay, in place of N2. Okay, clear?
Yes.
Right. So that's how you can get. And so let's this question we did.
Yes, sir, we did.
Yeah. Okay. And this one also we did.
Yes, sir.
Okay, good. So Sandmeyer and Getterman. Yeah.
No, sir, we have to do.
Yeah. This we did.
No, sir, we didn't.
Okay. So actually, there are two methods to put BR and CL. And what are the two methods? One is Sandmeyer and another is Getterman. So in Sandmeyer, what you take? In Sandmeyer, you take cuprous salts. Right?
Yes, sir.
Okay. Cuprous salts and HBr. Cuprous salt, sometimes it is written as Cu2 Br2. Right? So don't get confused. Cu2 Cl2, these are cuprous salt. Okay. And suppose if you want to put Br, what you can do? You can take CuBr2 or CuBr or Cu2Br2 and HBr. Right?
Yes, sir.
Here. So this is Sandmeyer. So Sandmeyer and so this can be written as Cu2Cl2, right? And HCl. Okay. Okay. Right. So this is Sandmeyer. You can this N2 will come out along with the leaving group, along with a pair of electron. and this N2 will come out, and the Br minus this from the Cu to Br2 will come and join at this position. Similarly, Cl will come and join at this position. In Getterman, you take only copper powder. Suppose if it is written as Cu powder, right, plus HBr. Okay, so then it is Getterman reaction. Just the difference of name. The purpose is same. Okay, right?
Yes, sir.
Purpose is same. Okay, the purpose is same. So Sandmeer and Getterman actually are the two methods which are used to attach Cl or Br to benzene via diazole. Okay, that you need to understand. Okay, another thing is uh, uh, another thing is actually, if copper powder is taken, then it is Getterman. Okay, this is applicable only for Cl and Br. Okay, right? Okay, clear? But how will you, so this is an actually extra method. Okay, because why it is extra method? Because you can attach directly Cl and Br. Okay, by taking Cl2 and FeCl3, right, or Br2 FeBr3. Okay, okay, but for fluorine, this is the only method. Okay, why this is the only method? Why you can't attach fluorine directly? Tell me why you can't attach fluorine directly. Yes, Amira, because fluorination is highly exothermic. Okay, okay,
Yes, sir.
okay. Fluorination is highly exothermic, so you can't attach fluorine directly. So how you attach fluorine then? Tell me how you attach fluorine. Yeah, tell me. You use Szechuan reaction. Okay, this you should remember. It is very very important. Okay, so Szechuan reaction is actually, it is a method which uses synthesis using diazonium. Okay, so what you do, you take benzene, you don't do fluorination directly. Okay, because fluorination is highly exothermic, uncontrollable, and once you attach fluorine, what will happen? The whole benzene ring will react in excess and it will break. It is very exothermic in nature. So what you do, you don't put fluorine directly. Uh, you first prepare diazonium salt from benzene by doing nitration, then reducing the NO2 group to NH2, making it diazonium. Okay, diazonium, and that diazonium is heated with fluoroboric acid. Okay, HBF4. Can you see? And how this HBF4 is made? HF plus BF3. Okay, so either it is written as HF plus BF3, or it is written as HBF4, it is one and the same thing, because F minus will come and join BF3, it will become BF4 minus, and H plus will come out. And when you heat it, okay, first when you heat it, look here, you can see the heating sign. So F minus, which was taken by BF3, will come out again, right? And it will go and attack at the site where N2 is connected. N2 will also come. And that's how you get fluorobenzene. Okay. Is it clear?
Yes,
Samira?
sir.
Yeah, very, very important. Fluorobenzene. So you have BF3N2, and this name is different. It is neither Sandmian nor Getterman. Okay. This is Shishman reaction. Bal-Shishman. Complete name is Bal-Shishman reaction. BALZ. Okay. Just Shishman is enough. Okay. And if you want to prepare iodobenzene, so fluorobenzene can't be prepared directly from benzene. So this is a very, very important process, because this is the only way to prepare fluorobenzene. Okay. Or reliable way. There are other ways also, but they are not in your syllabus. Okay. Whatever is there in the syllabus, how to follow this method, this is the only way to prepare fluorobenzene. Okay. It can't be prepared directly, because it is highly exothermic. Okay. So, and same is the case with iodobenzene. Iodobenzene, if you do the iodination directly, what happens is the reaction doesn't complete. Okay. And the reaction actually stops in the middle, because iodine is very, very less reactive. So iodobenzene also, instead of preparing directly from benzene, what you do, you first prepare a diazonium salt from a benzene by doing nitration reduction and reaction with NaO2 plus HCl, and that diazonium has N2, and you heat it with Ki. Okay, this Ki, once it is heated, it will I minus will come and attack, N2 will come out. Okay, and I minus will join itself to the benzene. Okay, this name is also neither Sandman nor Getterman. There is no name to this method. There is name given to the method to attach fluorine via diazonium, that is Shishman reaction, and there is a name given to attach chlorine and bromine via diazonium. Okay, either by using cuprous salt and HX, HBr and HCl, and that is Sandmere, or if you take copper powder and HCl or HBr, that is called Getterman reaction. Okay, is it clear?
Yes.
Okay. Yeah, very, very important. Yeah, so let's do some questions. Yeah,
Option C.
which of the following compound has to be used in Getterman reaction? Yeah, good. Option C. Very, very simple questions. Okay, just basic thing to make you revise, recall whatever we have studied. This one. And the diazonium salt is treated with dash, iodobenzene is formed.
Option A.
Yeah, Ki. Very good. Yeah. And which of the following is not produced when pH N2 plus Br minus, this is the diazonium salt, is warmed with Ki? Which of the following is not produced? That you need to tell me. Which is not produced? This is the method to prepare iodobenzene, right? And when you heat with Ki, you get iodobenzene, because I minus will come and attack on the benzene, and N2 will come out. Okay.
Option D.
Option D. Yeah, very good. Yeah, because you can think in this way. This is benzene. This is N2 plus. Okay. Yeah, correct. Let me give the answer very quickly. Though you are right, absolutely correct. K plus will form salt with Br minus. N2 will come out, and the whatever the Ki you have taken, that I minus is going to come and join itself to the benzene ring. Okay, so pH I plus N2 plus KBr. This you can't get. Okay, yeah, right. What about this one? So benzene diazoxide chloride is treated with dash, gives a product which on heating form fluorobenzene.
Option B.
Option B, yeah, correct. Fluoroboric acid, which is can be written as H plus and BF4 minus, or you can write it as a summation of HF and BF, right? So this thing, though we will get back to this topic in aromatic amines, okay, in phenols, okay, because it is a very important method to prepare compounds of benzene. The same Sandmeyer and Getterman can be applied for either fluoride, bromide, okay, and it can be applied for cyanide also. If Cn minus is there, if you take CuCN plus KCN, then it is Sandmeyer, and if you take copper powder plus KCN, it is Getterman. Okay, so you can prepare benzonitride PSCN also, but that is there in the aromatic amine chapter. We will come back to that. Okay, if you treat diazonium with water or dilute H2SO4, the water molecule will go and attack on the benzene and phenol will form. Okay, right? Phenol will form. So that we need to understand. But so it will be we will be discussing it again in the phenol chapter. Okay. So let me start a new type of reactions given by alkyl halides. Okay, and those new type of reaction, as you can see here, they are nucleophilic substitution reactions. Okay, so what substitution? What it means? What do you mean by substitution? You can tell me quickly.
Addition.
Yeah, it is actually one group displaces another. Okay, so that is substitution. Yeah. So have we seen any substitution? If you are aware, yeah, we have seen free radical substitution. Okay, when you treat methane with bromine, okay, in the presence of sunlight. So why that substitution was free radical, and why this substitution we will call it as nucleophilic? It is because the intermediates which are involved. Okay, when you treat chlorine or bromine with sunlight, it breaks and it forms radicals. Okay, free radicals. Okay, and that's why, so Br radical come and take away the H radical. The carbon radical is formed. The carbon radical will again attack some Br2 molecule to have to take away Br. Okay, so that's how you have this reaction. That reaction which we discussed, photohalogenation of alkanes. Okay, and that was free radical substitution. And this is nucleophilic substitution. So let me explain first before proceeding ahead. Let me tell you this alkyl halides, they are polar. Okay, why they are polar? Can you tell me quickly? They are polar because there is a polar bond. But why the bond is polar? It is because there is an electronegativity difference between the Br and the carbon. Okay, electronegativity difference means what? Actually, Br has more tendency to pull the electron cloud towards itself. So it pulls, this electron cloud is not in the middle, it is towards Br. So that's why Br will have partial negative charge, as you can see here, and the carbon will have positive charge. Okay. So this alkyl halides are polar, they have polar bond. And because of the electronegativity difference between the carbon and halogen, the carbon has partial positive charge. Okay, and this positive charge is actually an invitation to nucleophiles. So Samira, what are nucleophiles? Any idea? So nucleophiles are the species, they can be neutral molecule, they can be ions, which have unshared pair of electrons. Okay. Okay. So water is also a nucleophile. Why water is a nucleophile? Because it has unshared pair of electron which it can give, with which it can share with some other species. Okay, that's why it is called as a nucleophile. So nucleophile, the name indicate nucleus loving species, means these are the species which have electrons available, non-bonded electrons, okay, which are also known as lone pair, and they can share readily these non-bonded electron or lone pair with some other atom. But for that, very important, for that the other atom need to have a positive charge so that they can attract the nucleophile. Okay, is it clear? So that they can attract the nucleophile. So I hope it is clear to you.
Yes, sir.
So in this case, OH minus is a nucleophile. Okay, and it is going to get attracted towards CH3Br. Okay, but the problem is carbon can make only 4 bonds. Why it can make only 4 bonds? Because carbon is tetravalent. It is from the second period. It has only 2s and 2p. Okay, so it can make only 4 bonds, right? So if the nucleophile is coming and trying to join itself to the carbon, what will happen? Yeah, tell me. Yeah, someone has to leave. Okay, so if nucleophile is coming, someone has to leave. So who will leave? Okay,
Yeah.
yeah, Br will leave. Yeah, why Br will leave? Because Br is electronegative, it is larger in size, and its bond is weaker. It can break away more easily as compared to H, and that electron pair through which the Br is connected to carbon, that will be taken by the Br itself. Okay, why? It is because the nucleophile is bringing its own electron pair. Okay, and so the Br has to take the electron pair with itself, right? So actually if a nucleophile is coming, then a nucleophile it is bringing in the electron pair with itself. So the group which leaves, that has to take away the electron pair, okay, along with itself, bonded electron pair. And if the radical come, the radical leaves. Okay, if electrophile come, then the leaving group is also electrophile, because total number of electron need to remain same before and after the reaction. That's what the funda is. So the you can see the OH will get connected to the carbon and the Br will come out. So this is a nucleophilic substitution reaction, and nucleophile is responsible for carrying out this reaction, as you can see over here. Okay, so that's why it is called nucleophilic substitution reaction. Okay, so one group which is a nucleophile displaces another group, that is a nucleophilic substitution reaction. Okay, and the other thing is there are elimination reactions also. So what do you mean by elimination reactions? Yeah, tell me.
To
What is,
eliminate something.
Yeah, eliminate something means actually two groups are removed. Two groups are removed. Not one group. Two groups are removed, and no other group take their place. Take their place. So what happened to the bonds through which the two groups were connected? Are they going to remain as it is? Are they going to stay in the air without being connected to any other group? Because elimination means two groups are removed and no other group come and join in their place. Okay, so that's what elimination is. So whatever the two bonds, because two groups are removed, two valencies became free, and those two valencies of the two bond they will join among themselves only, and that's how you see there is a double bond formation, right? Is it clear?
Yes, sir.
So there is a formation of a double bond, that is elimination reaction. Okay, so it is actually the elimination of X and H minus H plus and X minus, okay, from adjacent atoms, right? So let's do this question. A very simple question, but very important, very basic. Okay, yeah, yeah. What will be the answer to this one?
I think option B.
Yeah, correct. Option D, the first option is elimination. You need to check the molecule, whole molecule thoroughly, and you need to find out what all groups are removed. So there is a Br which is removed and there is a H which is removed. So that's why you have a double bond. Okay, and this is substitution reaction, right? Very good. Because one group is removed, another group come and take its place. And this is addition reaction, addition of bromine. Addition and elimination are just the opposite to one another. Okay, they are completely opposite to one another. Okay, elimination means two group are removed. There is a double bond, and if there is addition, if it is addition reaction, then that double bond two groups come and join to that double bond. Okay, so this is D option is correct. Okay, so now the thing is how. So we will discuss first the substitution reaction, and there are two mechanisms. Okay, and the name also are written over here. Okay, you can see. So first we will discuss SN2 mechanism. So can you tell me what do you mean by the term SN2? Yeah, does it hold any significance for us? What does this mean? What is the full form of SN2? So it is a actually it is a substitution reaction. Okay, but how it is happening? Okay, that is explained by actual detailed mechanism by looking into the reaction in detail step by step procedure, and that is called mechanism. So mechanism, as on the basis of the mechanism, the substitution reaction is divided into SN1 and SN2. So let me discuss SN2 reaction first. Okay, so SN2 stands for that the complete full form of SN2 is substitution nucleophilic bimolecular. You can write. Okay, so it is substitution nucleophilic bimolecular reaction, and it is a single step reaction. Okay, so let's take some example. The example which we just now seen in the last slide, let's take that example again. I'm writing it again for the clarity. Okay, so this is the nucleophile. Okay, the reactant on which the nucleophile attacks, that is known as substrate. This is nucleophile. Okay, This is the product, and the substitution is completed. The Br minus is substituted by OH minus, and the Br minus is removed from the substrate, and this is known as leaving group. Okay, this is the product. Okay. So these are the terms which are used in substitution reaction, and this is the overall reaction. Okay, means just the reactants are written, products are written, that's it. But how it is happening, what is going on internally, okay, that is not mentioned. And on the basis of that internal mechanism, it has been assigned as SN2 mechanism, okay, which tells us that it is substitution nucleophilic bimolecular. S means substitution, N means nucleophilic. So first two letters are clear, substitution, because it is substitution reaction. Nucleophilic means nucleophile has attacked, okay, and that is responsible for the substitution reaction. And bimolecular, let me explain this term bimolecular. Okay, so how it happens. So this is the OH minus, okay, and this is the O minus, the red one. And the carbon, I already told you, it is polar bond. So there is partial positive charge, partial negative charge, okay. This O minus will come and join itself to the carbon. Okay, it will come and join, attack itself, because it will get attracted towards the positive charge, partial positive charge of the carbon atom. So it will come and join to the carbon. Okay, and carbon actually can make maximum how many? 4 bonds. Okay, so 5 bonds can't form. So if the OH is coming and trying to join itself to the carbon, this Br will come out. But how this is happening? What is the sequence of this attachment and removal? That we need to know. Okay, so SN2, you can write it as a single step mechanism. Okay, single step. So how it can happen that there is one group which is removed, one group which is added, and how all these things can happen in just one step. Okay, so this is possible if the nucleophile, it is general way of representing a nucleophile as Nu minus, comes and join itself to the substrate from the side opposite to leaving group. First thing is this one. You need to keep this in mind, because if one group is coming and another is leaving, they can't do it from the same side. Okay, so another point is single step. Single step means you can write the attack of nucleophile and the departure of leaving group take place simultaneously. Is it clear? Right?
So can you repeat?
The attack of nucleophile and the departure of leaving group take place simultaneously. Okay, and how the simultaneous arrival of nucleophile and departure of leaving group, how it is possible? It is possible by, if the nucleophile is coming from the side, from the back side, okay, or the side which is directly opposite to the leaving group. Okay, so you can see over here these dotted lines. So OH minus started giving its electron pair. It has started forming bond with the carbon. Okay, and simultaneously the Br minus, this is Br. Okay, this is dotted line again. It is trying to take away its electron and it is trying to come out. This bond is breaking. Is it clear?
Yes, sir.
Right? So this is how the reaction is happening. So, and this is known as transition state. It is known as TS. Okay. So in TS, you can see how the reaction starts. The nucleophile molecule collides with the substrate molecule, carbon, it's carbon atom of the substrate molecule. and it start forming its bond, it start giving its electron pair, and Br minus start coming out slowly. Okay, that's how the reaction start happening. Okay, but this is not a new step, this is just the picture of what is happening in that one step. The reaction is single step only, everything gets over in the one step. So but if someone asks you what is happening in that one step, can you tell me? So this is happening, this is known as transition state. And what happened to the groups which were not participating in the which were not participating in the reaction? Remember, there were 3 hydrogens CH3. They were not part of the reaction. So they were neither the part of the nucleophile, they were neither the part of the leaving group, they just remain on the carbon before and after the reaction. So actually what happens is, so carbon, so this side you have a leaving group. Okay, this side, if you have a leaving group on this side, the nucleophile will come from back side. Okay, and the carbon atom which were connected to the carbon, they will become flat. How they will become flat? The carbon will change its hybridization. Initially it was sp3. You might have studied in your 11th class chemical bonding chapter. Okay, sp3 tetrahedral carbon, and now it has become sp2. Sp2 is flat. Okay, is it clear? So it is flat carbon sp2, and by undergoing it, by making itself sp2, the carbon atom, because carbon atom has 3 p orbitals. Okay, no, so two of the p orbital and one s orbital undergo hybridization, they become sp2, and that is flat. Okay, and the another p orbital that carbon uses to accept electron, on one side this p orbital is accepting electrons from the OH minus nucleophile, and on another side this p orbital is actually giving away the electrons to the Br minus, which is slowly collecting its electron density and trying to come out. So when the reaction get completed, so this bond, okay, this becomes firm. Okay, the nucleophile is connected, this p orbital will get the electron density on this side, so it will form a bond on this side, and another side this loop will diminish. Okay, it will be reduced. It will be reduced. Why it will be reduced? Because the Br minus has gone out. Okay, so this is how this reaction has happened. Okay, there is a collision of 2 molecules. One is the nucleophile, another is the substrate, and then only the reaction starts. Okay, so that's why it is known as bimolecular. 2 species are involved. Okay, so I hope you understood the term. What does this term 2 means? And you can see the energy profile of this reaction. Okay, this is the transition state. Okay, this hump is indicating the energy profile. So when the 2 molecules come and they start interacting with each other, they are very close to one another, there will be an increase in potential energy. Okay, because the 2 molecules need to overcome their repulsive forces, then only they can come together and start reacting. Okay, so that's why you can see there is a hump. Okay, once the molecule crosses this hump, it just, the bond with the nucleophile become more and more stronger, and the bond with the leaving group will become more and more weaker, and finally in the product the leaving group completely gets separate. Is it clear? So that's how the reaction has happened. Okay, let me discuss some more features of this SN2 reaction. Okay, so just now you remember I told you that the attack of nucleophile take place from the side opposite to the leaving group. Okay, why it is necessary? Because actually both are taking place simultaneously. Okay, so in this case I minus has to attack from the side opposite to Br. Okay, actually it is written here, but it is actually, if you look at the mechanism, okay, so it has to come from the back side. Side which is back side means a side opposite to Br. So do you understand what is written over here? Just read it and tell me. Yes, Amira?
Inversion of configuration involved and inversion.
Yeah, inversion of configuration. Okay, so if wherever the leaving group is connected, that carbon is a chiral carbon which is connected to 4 different groups, you will observe inversion of configuration. Okay, so inversion of configuration take place in the SN2 mechanism, and this inversion is official name is Walden inversion if someone asks you, but most people say it inversion, but sometimes it is written, the complete name is written, that is Walden inversion. So be careful about that. Okay, it means the carbon atom which is chiral, okay, wherever the attack occurs, the bonds which were on this side, okay, it became like this. Okay, it is just like the inversion of umbrella. Okay, so sometimes what happens, suppose if you are carrying an umbrella in rainy season and there is a high speed wind blowing, so our umbrella gets inverted, okay, like this. In the same way, the 3 bonds which are not participating, which are neither nucleophile neither leaving group, okay, so their position get flipped, inverted. Okay, it is because the nucleophile will attach itself from the side opposite to the leaving group. So if the eye is coming from this side and the 3 groups were facing eye, so once the eye will get connected, so these 3 groups are facing the eye will come in the transition state, they will become flat, and the when eye will get connected completely, what will happen, these 3 groups will move to the other side. Okay, you can see now they are pointing on other side. So this means inversion, but it is not a matter of concern if it is not a chiral carbon. Suppose if it is a normal carbon, then it doesn't matter at all. But if it is a chiral carbon, or if there is some stereoisomer which is there, then you have to be very careful while choosing your answer. Okay, so what do I mean by when I say this? Let me discuss this next question. The methyl and bromine are both pointing upward, and the upward is indicated by the solid wedge. Okay, they are cis. They are both pointing upward. Okay, and if you take OH minus, what will happen? The OH minus will come, because as just now we discussed, it is SN2 reaction, so it is mandatory for the nucleophile to come and attack from the back side, otherwise it can't happen. Okay, so from which side the OH minus will attack the ring? Is it from the top side or the back side, bottom side? It is from the bottom side, because Br is at the top, Br is coming out of the plane, so OH minus will come and join itself from the lower side. Okay, so finally you will see the change, the Br will come out and the OH will get attached from the side, lower side. Is it clear?
Yes, sir.
So you will see, so there is an inversion of configuration, but you will notice that the product was having a cis isomer, but now this one is having the product, the reactant was having a cis isomer, the product is having trans isomer. Okay, is it clear? So be careful regarding that. So question can come to you in this way also. Okay, and the Br is pointing upward, as you can see. So this is a nucleophile SET minus, this is ethyl S minus, so S is the nucleophile, it will come and so Br is upward, so that S minus will come and attack on the carbon atom from the lower side. Okay, from the back side or the side behind the plane of the paper. Okay, so finally you will have SET group connected to the carbon, you can see, but it is indicated by dash, means it is attached itself. So what you need to do, you don't have to write, get into the complete mechanism, write all the details of the mechanism. You need to take care, you need to look at the product and the position of the leaving group very carefully. So if the leaving group is pointing above the plane of the paper, which is indicated by the solid wedge, you will put the leaving group if it is SN2 reaction. Okay, be careful. If it is SN2, then only you need to do this. So you will attach the nucleophile from the, so if the leaving group is up, you will bring the nucleophile from the bottom side, and the nucleophile will point itself towards, will be represented by this dash, which says that the nucleophile is attached from the side opposite to leaving group, means backside. Okay, so if BR is up, pointing upward, you will attach this nucleophile from the behind, okay, from the side opposite to the leaving group. Okay, so I hope you understood how you need to attempt these problems, because these problems are asked in all the examinations. Okay, they are very simple, but you need to be very cautious while drawing the structure. That's the only precaution you need to take. Okay, so we discussed the mechanism of SN2 reaction, just a quick overall profile of the mechanism. Now let me tell you more details of the SN2. Okay, so how the speed of SN2 will depend. SN2 was a biomolecular reaction, just now we discussed, and it started with the collision of two things together. And what were those two things? Right? What were those two things? The two things were the nucleophile and the substrate, right? So when they collided, then only the reaction started, then only the transition state appeared, in which there was a simultaneous bond breaking and bond forming. Okay. So the speed of SN2 reaction will depend upon the concentration of both the nucleophile as well as the concentration of the reactant or the substrate, which was alkyl halide. So suppose if you, why, or you can understand it in another way. Suppose if you have more concentration of nucleophile and substrate, the chances of collision are going to increase. Probability of collision, more collisions can happen between them if their concentration is more. Means more number of nucleophiles, more number of substrates are present in 1 liter of solution. So definitely the rate will increase. Okay, so I will say that the rate of SN2 or the speed of SN2 is directly proportional to the concentration of Rx into concentration of nucleophile. Okay, and if you remove this proportionality constant, you will put constant K. Okay, proportionality sign, you will put a constant K, and this is actually known as second order reaction. What do you mean by order? Order is actually the sum of the powers of the concentration term. Okay, as the rate was dependent on both the concentration of substrate as well as on the concentration of nucleophile. So actually the it was a second order reaction, means there were two concentration terms. Okay, so if you double the concentration of substrate, what will happen to the rate of speed of SN2? Samaira, can you tell me quickly?
The rate will decrease.
Rate will decrease, or will it come down, or will it go up? If you increase the concentration of alkyl halide, will the reaction become faster or slower?
Slower.
Why? Just whatever you think, you can tell me. Yeah. If you increase the concentration of substrate, okay, will the reaction become faster or slower? It will become faster. Okay, because if you have more substrate molecules, okay, means more collision can happen because they are more in numbers. So more nucleophiles can come and attack them. Is it clear?
Yes, sir.
If you have less and less substrate molecules, mean the chances of the collision between the substrate and the nucleophile are decreasing. Okay. So if you increase the concentration of substrate, if you double the concentration of the substrate, the rate will become double. Okay, because you are increasing the chances of collision. And until unless the collision happens between the substrate Rx molecule, the alkyl halide molecule, and the nucleophile molecule, the reaction is not going to happen. The substitution is not going to happen. So if you are increasing the concentration, means you are increasing the rate. You are making the reaction faster if you are increasing the concentration of any one of them or both of them. So suppose if you double the concentration of nucleophile, then what will happen to the speed of reaction? Rate means speed. Okay, what will happen to the rate of SN2 reaction? Will it get doubled? Will it get halved? Or will it remain unaffected? If you double the concentration of nucleophile,
It will double.
yeah, it will get doubled. Yeah. Because if you have double concentration of nucleophile, suppose instead of 1 molar, if you take 2 molar, definitely, because in the reaction these nucleophile molecules are moving randomly, and because you have increased the number, definitely there will be more collisions, and the number of collision will be double the number of collision which were happening with 1 mole per liter. Now it is 2 mole per liter, so the number of collisions have doubled. Okay, and if you double the concentration of both alkyl halide and the nucleophile, then the rate of SN2 will become 4 times. Okay, because twice into twice. Okay, if you increase both of their concentration, then it will become four times. Okay, so this you should keep in mind, right? So because a lot of questions come, but this is very simple, and there is a complete chapter, chemical kinetics, dedicated to understanding of speeds of chemical reaction in 12th class only. Okay, so we will discuss that in detail, but as of now, for SN2, this much is enough. Okay, and so there are other factors also which affect the rate of speed of SN2 reaction, and the other most important factor is the nature of the alkyl group of the substrate itself. So alkyl halide are Rx, okay, and what that R was, how much branch it was, okay, that that will tell you that whether the reaction is going to happen quickly or slowly. Okay, so relative rate of SN2, if you have methyl, ethyl, propyl or isopropyl, and this is tertiary butyl, the rate is going to decrease. So you can write rate of SN2 decreases with branching. Okay, so methyl is fastest. If you have same leaving group, okay, leaving group also you can change. That will also affect the rate of SN2. But here you have same Br leaving group, and if you keep all the concentration same, just you change the substrate, then as the substrate is going to become more and more branched, the rate of SN2 decreases. Okay, it becomes slower and slower. So can you tell me what could be the reason for this? And you can note down on the tertiary alkyl halide, there is no SN2 reaction. Okay, no SN2 on tertiary alkyl halide. Yeah, tell me. Yes, Amira. Why decreases? Am I audible?
Yes, sir.
So why decreases? Tell me. Actually, so you should you just now we discussed the transition state. Okay. So look at the transition state more closely. These were three hydrogens. Okay, we took this CH3. Okay. So but if you are taking ethyl bromide, what will be the picture? This picture will become like this. Instead of three hydrogen, you need to put one CH3 group in place of that one hydrogen. Do you agree with this?
Yes, sir.
Okay. And if you take isopropyl group, which is a secondary carbon, then you will put one more methyl at this position. It will look like this. I will draw it separately. This is isopropyl bromide. And if you take tertiary butyl, then it will be like this. Means if we are making the carbon primary, from methyl we are changing it to primary, secondary and tertiary. It means what? It means we are increasing the number of branching. We are increasing the steric hindrance or the repulsion for the incoming nucleophile. Okay, clear. So this nucleophile will face more and more difficulties to come and join itself to the carbon. Is it clear?
Yes, sir.
If it is tertiary, then it will become very difficult for the nucleophile to come and get into the between through these hydrogens and push away these groups and access the carbon atom on which the bromine is connected. It becomes very difficult. So tertiary alkyl halide will not undergo SN2 reaction. You can write that rate of or speed of SN2 reaction decreases with the increase in branching on the substrate. That you can note down. So if it is SN2 happening and if there are two substrates, one is more branched, another is less branched, okay. One has more alkyl groups, another has less alkyl groups. The speed is going to be faster on the substrate which is having less number of alkyl groups, less crowding. Okay, there the reaction is going to be faster. Okay, the rate depends upon the leaving group also. Okay, so we will understand it through questions. Okay, so let's do this question. Very basic, just a collection of points of characteristics of SN2 reaction. What all options are correct?
Option D.
Option B. Yeah, the rate of SN2 is independent of the concentration of nucleophile. No, never. It is incorrect. The nucleophile attacks the carbon atom on the side of the molecule opposite to the group being displaced, side opposite to the leaving group. Yeah, this is correct. And that's why the Walden inversion happened. That's why the inversion of configuration happened. Okay. The reaction proceed with simultaneous bond formation and rupture. Is this true or false? Yeah, tell me, Samara, for SN2 reaction. This is true because it is simultaneous bond formation and rupture. Okay, so the second one is true. The third one is true. First one is incorrect, and this is also. So the answer is going to be B and C. Is it clear?
Yes, sir.
Okay. And this is a bit more difficult, but you can try and you can do it. So let's try it. Yeah. So this is also one or more than one correct. A very important question need to be discussed in detail. Yes, Amira is the first one correct. It is the effect of leaving group. So if you have same alkyl group, will the nature of leaving group affect the rate of SN2 or will it not affect the rate of SN2 reaction? What will you say? Will the reaction get affected or will it not get affected? So think, if everything is same and the leaving group is different, so think, and the leaving group is also coming out in that same step in which the nucleophile is attaching itself, because it is SN2, it is simultaneous arrival and departure. So does the strength of the leaving group matter? The answer is yes. It is because this Br is bigger and it is farther. Its bond is weaker. Its bond is longer. It can break more easily as compared to Cl, which is smaller. Okay. So leaving group tendency of halide, you need to think about the leaving group tendency only if the alkyl groups are same. So leaving group tendency. F minus Cl minus is a better leaving group. Br minus is better than Cl minus, and I minus is much better leaving group than all of these halides. Okay, is it clear?
Yes, sir.
Because of the longer bond, weaker bond, they can come out more easily. And you can also note down weak bases are good leaving group. Okay, so how you are going to, suppose if there is a confusion, you can just note it down. Weak bases are good leaving group everywhere in all organic. You can uh, remember, rely. Sorry, you can rely on this statement that weak bases are good leaving group. Okay, and how you are going to make out whether something is weak or something is strong? Very simple. Okay, so suppose you can make acids out of those HF, HCl, HBr, HI. Okay, so HI is strongest acid. Again, the reason is same, because H plus is very small, I is very big, and it is going to break away more easily. So strong acid will have weak base, conjugate base, weak base, and weak base means stable, and stable means it can come out, it can leave very easily. Okay, it can come out very easily, and that's why weak bases are good leaving. You should keep in mind, very important thing. Okay, or you can, if you are confused, suppose if nothing is working, you can also compare the bond strength. You do not have to remember the actual bond energies. You can just compare which one is longer, which one is shorter. This is going to be weaker, the longer one is going to be weaker, it is going to break away more easily. So this is faster. Okay, so let's read the statement. propyl chloride will react more readily than propyl bromide in SN2 reaction if all the rest of the things are same. Okay, though they are not written, but you should keep in mind if nothing else is asked, means that it is assumed that rest of the things are same, means nucleophile is same. Okay, the temperature is same, the concentration is same. Okay, so this is incorrect statement, because ethyl bromide is going to react more quickly because bromine is a good leaving group. Is it clear or not?
Yes, okay.
So leaving group tendency affects the rate of SN2 reaction. Better leaving group means faster rate of reaction. Okay. The next thing is this propyl iodide, N-propyl normal propyl iodide will react more readily than isopropyl iodide, which is a secondary compound for SN2 reaction. Is this correct or incorrect?
Incorrect.
Just think it. This one will react more readily. I will draw them again separately. This is primary halide, and if the nucleophile is attacking at this carbon has only one alkyl group and two hydrogen. Hydrogens are very small and they will not pose any steric hindrance for, or very less steric hindrance towards that incoming group, being very small groups. And if you take isopropyl iodide, so if the nucleophile is approaching the carbon, okay, this carbon is connected to only one hydrogen and two methyl group. These methyl groups I have written them in condensed manner as CH3, but those 3H are also, these 6H are also coming out like this. They are spreading. So this is secondary. This is primary. Now tell me which one do you expect to react more quickly in SN2 reaction? Now just think it. No matter if it goes wrong, don't worry about it. Yeah.
The primary.
Yeah, primary. Yeah, exactly. So methyl one for SN2 methyl halides or the methyl substrate are going to react in with fastest rate, assuming that all the rest of the things are same. They are not changing. Okay. So methyl is more reactive than 1 degree. 1 degree is more reactive than 2 degree and 3 degree. As you have more and more branching, the rate of SN2 is going to become lesser and lesser and lesser. Okay. So this react more rapidly. Propyl iodide, yes. Propyl iodide is primary, and this is primary carbon. Okay, it has two hydrogen. Hydrogen are very small, so it is going to react more vigorously than the secondary one. Okay, which is more branched, more alkyl group, more hydrogens on those alkyl groups will stop the nucleophile. Okay, will stop the attack of nucleophile. So that's why the rate is going to be slower. What about this C option? Here the leaving group is same, Br and Br. So this propyl bromide will react more readily than this is neopentyl bromide, the common name. Or if in case of any confusion, what you can do is you can write their detailed structure. Yeah, which one do you expect? This is neopentyl. Okay, do remember the common name. Now I will tell you why it is very famous. Neopentyl because there are overall 5 carbon atoms. Yeah, which one is going to be faster?
First one.
Yeah, first one. Yeah, and there is a very famous question in all the books, even in NCERT. They will tell you that neopentyl chloride or bromide. They are primary. Okay, because this is primary carbon. But in spite of being primary, this is also primary. Neopentyl halides are almost unreactive or inert, almost inert towards substitution reaction, SN2 reaction. Why? Though they are primary and the steric hindrance is very less on primary, you expect the nucleophile to come and attack on this carbon. But why the thing is actually happening, not happening in a way in which we are thinking. It is the question given in all the books, right from NCERT to all the foreign other books. Okay, Solomon's, Carey, and all the books, right, of organic chemistry. They ask this question. So, yeah, the answer is this is primary, but it is still very bulky, and the branching is not far away from the site where the actual reaction is happening. Though the branching is not directly at the position where the reaction is happening, but it is not far also. It is just on the adjacent carbon, right? So if you look at its picture, there are 2 hydrogens. That will make us comfortable. Oh, now the reaction can happen very quickly. But look at the other carbon. That other carbon is too bulky, too crowded. Okay, this is how it will look like. This is the BR. Someone say it is primary and it has no branching, but the branching is there on the molecule, not directly on the carbon atom which is connected to the living group, but on the adjacent carbon atom. So again, what is going to happen? The reaction is not going to happen. Okay, because all these groups, okay, you can see these many groups. Okay, I hope you are able to see. Okay, if there is confusion, you can stop me and you can ask me any number of times. Okay, so these tertiary group will block the attack of nucleophile. So SN2 is not going to happen. Okay, right? Clear?
Yes, sir.
Okay, now the next thing is what about this? What about this last? This this question is very big question and very important also. Yeah, what about this last option? Tell me. This is very difficult, and many of my JEE students are also not able to answer. Let me tell you. Okay, this is a benzene. These are benzylic substrates. Okay, how they will look like? So they look very similar. They look, and someone may think that there is a difference of groups on both of them, but those groups which are different are very far from the site of reaction. SN2 is happening at this point. So it may appear that these groups may not be affecting the rate of SN2. Okay, but this is not true. these groups will affect the rate of SN2. And how will they affect the rate of SN2? Actually, you need to write their resonance structures. And when you write the resonance structure, you will notice that there is a minus charge which will appear because the O has lone pair. That lone pair will get into the ring, delocalize with the ring. It will push the pi electrons of the benzene ring, and that's how it will get mixed up with the benzene ring. And the minus charge will appear on due to resonance structure. If you have any doubt in the resonance structure, do tell me. Okay. So this is going to be the resonance structure. So we are interested at this point. So this point has now become more negative because of the resonance of OCS. Okay. So if it has become more negative, what it means? It means the carbon which is having the Dr, that will also become more negative. Okay. And if it become more negative, will it facilitate the attack of nucleophile? The answer is no. Because nucleophile itself is negative, and if there is electron donating group already present, that is not going to help the attack of nucleophile. Okay. So how can you make nucleophile, how can you welcome the nucleophile more? Okay. So this is NO2. And if you look into the detail of this group, this NO2 group doesn't have any lone pair. It is having a plus charge. And this plus charge attract the electron pair of the benzene. So benzene will have plus charge at the ortho position, para position. And another ortho position, this is known as resonance effect minus R. So groups which are pulling electron because of the resonance are known as group exerting minus R. So if this is plus, this is going to attract this is going to make this carbon more positively charged. And more positive charge means more invitation to incoming nucleophiles. So the reaction is going to occur more quickly on this. So this will react more readily? No. Okay. So this is going to react more readily. Okay. So this is incorrect. Okay. So B and C options are correct. This is a very important question and we discuss a lot of aspects of acid. Is it clear? Any doubt in this, Samira?
No, sir.
It is a difficult question also. Okay, so be careful about this, right? So SN2 reactions are, we have seen many substitution reactions, and sometimes there are questions, there are two types of questions. Okay, there are questions like these one. Okay, like this. These are the questions which require the deeper understanding of the mechanism of the reaction. You need to know what is happening inside the reaction, then only you will be able to answer these questions. Okay, these are mechanism based questions. But there are a lot of questions which do not deal with the mechanism. There you just simply write the nucleophile or the reactants and you need to make the product. They are just for the conversion purpose. Okay. So how will you convert alkyl halide to an alcohol? Okay. So you need to substitute the Cl by OH. You need to do substitution reaction. OH minus you can take by taking aqueous KOH. The OH minus will attack. Okay, the OH minus will attack the carbon atom bearing the Cl minus, and the Cl minus is a leaving group. Okay, you don't have to just say it again and again. Just you need to write the product. Okay, this is the preparation of alcohol from alkyl halide by substitution reaction. Okay, OH minus is the nucleophile, right? If you take SH minus, then also the reaction is going to happen. Okay, because O minus, O and S are one below another in the same group. So S minus is also a nucleophile. Okay, SH minus is going to attack. Okay, and Br minus is going to come out. So in the first case you are having alcohol. The second case is the preparation of thiol. Thiols have same formula as alcohols, but instead of O you have sulfur, so thiol means it is alcohol made up of sulfur. Okay. Suppose if you take alkoxide ion, can you give me some name of the alkoxide ion? Formula of some alkoxide ion, like CH3O minus. This is the methoxide ion. Okay, you can take ethoxide ion, CH3, CH2O minus. So this is the nucleophile. It is going to come and attack on this. I minus is going to come out. So OR is going to attach itself to the substrate. Okay. So this is actually the substitution reaction. And but in this substitution reaction, you have taken one alkyl halide and one alkoxide, and you ended up with an ether. Okay, ether is having two alkyl groups on both the sides. And this is a very important reaction for the preparation of ether in the next chapter. It is known as Williamson ether synthesis, in which ethers are prepared by attack of alkoxide ion on alkyl halide. Okay, right? Williamson ether synthesis, very, very important reaction. It is SN2 reaction. Okay, so SN2 reactions are not only for alkyl halide, they are actually general reaction prepared used for the preparation of many other functional groups. Okay, RS minus is there. Br is going to come out. This is thioether ether made up of sulfur. Okay, if NH2 minus is there, the Cl minus is going to come out. You have amine, and you can take ammonia also. Okay, if you take KCN, Cn minus is going to come and join itself to the substrate, and I minus is going to leave. It is, you will have a nitrile. If you take this alkyne group, okay, having minus charge, this alkyne group will come and join itself to the alkyl halide, and that's how you have a bigger alkyne. You might have studied in your class 11th, okay, step up of alkynes. Okay, these are all the SN2 reactions commonly used SN2 reaction, but the purpose of asking these SN2 reactions will be to know whether you can write the product or not, or the purpose is just the conversion from alkyl halide to some other functional group. That's it. But the purpose of such questions, this question or this one, is different. They want to analyze whether you know the details of the reaction or not. Okay. And this is the whole list of nucleophiles and the substitution reaction. So where have you seen this list? First tell me.
It's there in the text.
Yeah, it is there in the NCRT. Yeah, it is from the NCRT. Yeah. So it is actually not only related to the alkyl halide chapter, but it is all these reactions will be useful for in your alcohol chapter, amines chapter, okay, esters. Okay, so this is the list of nucleophile. OH minus. And how you are going to take this OH? We write OH minus, but actually we need to take either NaOH or KOH, because you can't get simply OH minus, okay? Because it is unstable. It is a base. So OH minus will come and attack here. X minus will come. You will have ROH as the product, okay? And alcohol. This is the preparation of alcohol. You can take water also. Then also you can get alcohol. But water is a slow. The process will be slower because water is neutral. Okay. You can take R-O minus. This is alkoxide ion. By taking this Na plus and OR minus, OR dash minus. So this alkoxide ion is going to go and attack on the alkyl halide. This is alkoxide, means this is the nucleophile alkyl ROR dash will form. This is ether and this is Williamson ether synthesis. That's what I told you. If you take NaI or Ki, the Cl or Br are going to come out and I will get attached itself to the alkyl halide. This is Finkelstein reaction. If you remember, we prepared alkyl iodides and fluorides. Alkyl, aryl iodides and aryl fluorides we prepared by heating disonium with K ions HBF. But alkyl halides. In alkyl halides, the alkyl iodides were prepared by Finkelstein and alkyl fluorides were prepared by Schwarz reaction. Okay, just try to recall that what we studied. Okay, right? So this is the thing, alkyl iodide. If you take NH3, this N has a lone pair, it will attack on Rx, and you have primary amine. Okay, these are all are amine. This will give you secondary, tertiary. All of these we will study in detail in your amines chapter. But the mechanism is same as N2. If you take, this is very important. Okay, so first of all, tell me, so Cn minus, let me tell you, okay, the Cn minus is ambidentate nucleophile. What do you mean by ambidentate nucleophile? Means it has two lone pairs on two different sides. Okay, you can see over there. So it can attack the Rx, Ri from carbon side, but normally the carbon side attack, or it can come and attack from the nitrogen side also. So it is like this, either carbon will join or nitrogen will join. Okay, that is very important. Okay, but who will join when? So if you have taken KCN, KCN is K plus and Cn minus. K plus will get separated, C minus will attack normally, because C minus is more negative and it is more unstable. So carbon has more tendency to join and become neutral. So you will end up with RCN. Okay, RX, X will come out and CN. Are you getting it, Samira? Very, very important, right? And if you take AgCN, this is a covalent bond. So carbon is involved in covalent bond, it is not able to attack, nitrogen will attack. So you will get isonitril. Similarly for this, you can just go through them and let me know. In the next class we will just report.